You hear it every morning. That alarm cutting through the dark, your hand reaches out, muscle memory, and slaps that button. 9 more minutes, then 9 more, then 9 more again. Your partner rolls over, annoyed. Your roommate texts you from the next room asking if you even remember hitting snooze. And somewhere in your head, a voice whispers that you're lazy, undisciplined, that successful people wake up at 5 a.m. and run marathons before breakfast. But what if that voice is wrong? What if your brain, the one reaching for that button in the fog of morning, is actually doing something clever, something most people don't understand? They tracked 1,732 people first, mapping their morning habits. 69% hit snooze. Not occasionally, regularly. These weren't outliers, these were the majority. Then came the lab work. 31 habitual snoozers, polysomnography running all night, watching every brainwave, every eye movement, every breath. The protocol was brutal in its simplicity. Some nights they slept through. Other nights they got woken 30 minutes early, then hit snooze every 9 to 10 minutes until their actual wake time. Then came the cognitive tests, addition tasks, memory recall, reaction time, processing speed. The results? Snoozers performed better, not worse, better. Arithmetic accuracy jumped, working memory held strong. The sleep inertia that typically crushes your brain right after waking? Reduced, not eliminated, but softened. The snooze button, that thing you've been told makes you lazy, was actually making your brain sharper. From the Department of Clinical Neuroscience at Karolinska Institutet, and the Sleep Journal study from University of Notre Dame published October 2022, tracking 57% of participants as habitual snoozers using wearable biosensor data across multiple sleep cycles. Now back to the information. Your prefrontal cortex, the part that handles decisions, planning, controlling impulses, working memory, that region goes offline during sleep, deep offline. When you wake up, it doesn't just switch back on like a light, it crawls back. Studies using positron emission tomography at Walter Reed Army Institute of Research in 2002 tracked cerebral blood flow after awakening. Thomas Balkin and his team found that blood flow to the lateral prefrontal cortex stayed reduced for 5 to 20 minutes post-wake. Executive function, the thing that lets you think clearly, stayed impaired. The prefrontal regions took longer to reactivate than any other brain area, longer than the motor cortex, longer than the sensory regions. Your decision-making hardware is the last thing to come back online. The brain during sleep looks nothing like the waking brain. Non-REM sleep, stages 2 and 3, your neurons fire in slow synchronized waves, delta waves, 0.5 to 2 Hz, massive coordinated pulses across entire regions. It's energy conservation, the brain running on low power mode. And when that alarm goes off during stage 3, during slow wave sleep, your brain has to shift from those deep synchronous oscillations to the fast, chaotic patterns of consciousness. It's like asking a freight train to instantly become a Formula One car. The transition is violent, neurologically expensive. And when you're yanked out of stage 3, the sleep inertia hits harder. Studies using electroencephalography show beta activity, the fast waves associated with alertness, stay suppressed for minutes after awakening from deep sleep. Meanwhile, delta activity, the slow sleep waves, persists in posterior brain regions. Your occipital cortex, the visual processing center, holds onto sleep patterns even while you're technically awake. You're a chimera, part sleep, part wake, neither fully online. The snoozers spent more time in stage 1, lighter sleep, and less time in REM. Only 6 minutes of total sleep time lost. 6 minutes. In exchange, they dodged the brutal wake-up from slow-wave sleep. The alarm went off during lighter stages. The transition was gentler. The brain didn't have to make that violent shift from deep delta waves to beta consciousness. It surfed the lighter stages, easing into wakefulness over 9-minute intervals. By the time the final alarm rang, the brain was already halfway to conscious. The prefrontal cortex had time to ramp up blood flow gradually. The adenosine that builds up during sleep and causes that groggy feeling had time to clear from receptors in smaller waves instead of one massive hit. Energy. ATP. When ATP breaks down, it releases adenosine as a byproduct. The longer you're awake, the more adenosine accumulates in your brain, particularly in the basal forebrain. Adenosine binds to A1 and A2A receptors on neurons. Those receptors, when activated, suppress neural activity. They make you tired. They push you towards sleep. During sleep, adenosine levels drop. The brain clears it out. But right when you wake up, there's still adenosine hanging around. It takes time to fully metabolize. That's part of sleep inertia. Caffeine works by blocking adenosine receptors, preventing adenosine from making you feel tired. But if you hit snooze, you're giving your brain time to naturally process that adenosine without chemical intervention. The intermittent awakenings, those brief moments of consciousness between alarms, might actually help. Each microwake could trigger small clearance events, little pulses of adenosine metabolism, so by the final alarm the load is manageable. The meta-analysis from Francis Prekel and colleagues in 2011 examined studies on circadian preference and intelligence. Evening preference correlated with higher cognitive ability. The correlation was small, R equals 0.08, but consistent across studies. Morning preference correlated negatively with cognitive ability, R equals negative 0.04. Another study published in Intelligence Journal in 2014 looked at MBA students at the University of Chicago Booth School of Business, high achievers. GMAT scores in the stratosphere. The evening types scored higher on the GMAT. The pattern held even when controlling for sleep amount and study effort. Night owls weren't sleeping less or studying more. They just performed better on high-level cognitive tasks. The mechanisms are murky, but theories exist. One hypothesis, the training effects theory, suggests that evening types spend their entire lives fighting social systems designed for morning people. School starts early, work starts early. The world runs on morning time. Night owls constantly have to override their biological rhythms, constantly have to problem solve their way through a misaligned schedule. That chronic mismatch might train cognitive flexibility. It might build working memory capacity, because they're always holding two time systems in their head, their biological clock and society's clock, constantly reconciling the two. Another theory points to evolution. Night owls staying active late might have provided an evolutionary advantage in ancestral environments. Someone needed to watch the camp while everyone else slept. That role required vigilance, pattern recognition, threat assessment, cognitive demands that selected for intelligence. The correlation between eveningness and dark triad personality traits, narcissism, Machiavellianism, psychopathy, has also been documented. The darker aspects correlate with eveningness and with strategic thinking, exploitation, manipulation. Not moral, but cognitively demanding. The night is when predators operate. The night is when fewer eyes watch. If you're active then, you'd better be smart. When they looked at chronotype, the biological sleep-wake preference, there was no difference. Mensa members weren't biologically night owls. They had the same chronotype distribution as the general population. The late sleep timing was entirely explained by later work start times. High IQ individuals tend to end up in jobs with flexible schedules, creative fields, research positions, entrepreneurship, roles where you're not clocking in at 8 a.m. sharp. They sleep late because they can, not because their biology demands it. The genetic correlation between high IQ and eveningness isn't about biology. It's mediated pleiotropy. The genes that produce high intelligence lead to environments with flexible schedules, and those environments allow later sleep, and later sleep gets coded as evening preference. Remove the work schedule, look at free days, and the chronotype difference vanishes. But the snooze behavior persists. Stephen Mattingly at University of Notre Dame published in Sleep Journal in October 2022 the most comprehensive examination of snoozing behavior to date. 57% of working adults in the sample were habitual snoozers. That's more than half. The study used wearable devices, tracking heart rate, movement, skin temperature across hundreds of nights. Snoozers weren't sleeping less overall. They weren't taking more naps. They weren't reporting higher daytime fatigue. The snoozing wasn't compensation for sleep deprivation. It was a behavioral pattern independent of sleep quality. Younger individuals snoozed more. Women snoozed more than men. People with lower conscientiousness, one of the big 5 personality traits, snoozed more. People with evening chronotypes snoozed more. And here's the critical finding. Snoozers had lighter sleep in the last hour before wake time. Their heart rate variability, a marker of autonomic nervous system activity, was different. Even on nights when they didn't snooze, their pre-wake sleep was lighter. The brain was already preparing. The sleep architecture was already shifting toward a gentler transition. It's a pattern that starts hours before. The brain of a habitual snoozer begins lightening sleep in the final hour, reducing slow-wave sleep, increasing stage 1 and stage 2, positioning itself for intermittent awakenings. It's predictive. The brain has learned. You're going to hit that button. Your motor cortex is going to execute that movement. Your auditory cortex is going to register the alarm, but not fully engage the arousal system. The body is going to stay in bed. The system has adapted. And that adaptation might be protecting cognitive function. And 25 minutes later, the default mode network, the network active during rest and introspection, stayed hyperconnected with task-positive networks right after awakening. The dorsal attention network, the salience network, the sensory motor network, all the networks that should be segregated, should be operating independently, they bled together. The functional segregation that defines a fully awake brain was gone. People awakened from stage 3 showed the most dramatic loss of network segregation. They made more mistakes on cognitive tasks. Their EEG showed persistent delta power. The slow sleep waves correlated with the loss of network segregation. The brain was awake, but the architecture was still asleep. The boundaries between different functional systems hadn't reestablished. If the awakening happens during lighter sleep, the networks are already more segregated. The default mode network isn't as deeply entrenched. The transition preserves more of the functional architecture. You lose 6 minutes of sleep time, but you gain a brain that's closer to its operating specifications. The cognitive tests back this up. Sunderland's snoozers showed no impairment on most tests and improvement on some. The arithmetic task, which requires sustained attention and working memory, showed the biggest benefit. That's a prefrontal task. That's the thing that should be most impaired by sleep inertia. But it wasn't. The snoozing protected it. With it, while you solve problems. It's limited capacity. It's effortful. It's dependent on prefrontal cortex function. If snoozing protects prefrontal function by easing the transition from sleep to wake, and if smart people are more likely to snooze because they have flexible schedules and evening-leaning preferences, even if not true biological night owls, then snoozing becomes a cognitive tool. An optimization, not a moral failing. Not a discipline problem, a strategy that preserves the brain regions most critical for high-level thought. But chronotype mattered more than duration for some outcomes. Evening types scored 13.5% higher than morning types on cognitive tests in one group, 7.5% higher in another. Intermediate types, people with no strong preference, scored 10.6% and 6.3% higher than morning types. The morning people consistently scored lowest, consistently, across every cognitive domain tested. The pattern was robust. The effect size was not trivial. The researchers concluded that chronotype affects cognitive function, not just performance at different times of day, but baseline ability. The brain you have is shaped by when you prefer to be awake. Evening preference correlates with higher cognitive test scores. Therefore, snoozing correlates with intelligence. But correlation isn't mechanism. What's actually happening? They've noticed that when the alarm catches them in REM or stage 1, they feel more alert. So they engineer it. They set the first alarm early, giving the brain time to cycle out of slow-wave sleep, then snooze until they've naturally progressed to a lighter stage. It's self-experimentation. It's empiricism applied to personal sleep architecture. And intelligence correlates with metacognition, with thinking about thinking, with optimizing systems. A smart person treats their sleep like code to debug. If intelligence correlates with specific adenosine receptor polymorphisms, particularly ADORA 2A variants, then the snooze behavior could be compensatory. A brain with high adenosine load needs more time to clear it upon waking. Snoozing provides that time. The intermittent exposures to wakefulness, 9-minute intervals of consciousness, could trigger repeated adenosine clearance events, each one small enough to not fully wake you, but large enough to metabolize some of the accumulated adenosine. By the final alarm, the brain has processed enough to function. It's a biological workaround for a genetic reality. The prefrontal cortex in particular relies on long-range connections to posterior regions, to temporal lobes, to parietal cortex, to subcortical structures. Those long connections are metabolically expensive. They require more ATP. They generate more adenosine. They're also the most vulnerable to sleep inertia because they're the last to come back online. Blood flow studies show prefrontal regions lagging behind. If intelligence is tied to robust prefrontal networks, then protecting those networks during the vulnerable wake transition becomes critical. Snoozing protects them. It gives them time to reestablish connectivity without the shock of an abrupt wake. High conscientiousness correlates with morning preference. High conscientiousness correlates with waking immediately when the alarm sounds. High conscientiousness also correlates negatively with intelligence once you control for academic achievement. Smarter people tend to score lower on conscientiousness. They're less rule-bound, more willing to deviate from prescribed behavior, more skeptical of authority. The snooze button is an act of micro-rebellion. It's saying no to the alarm, no to the schedule, I'll wake when I'm ready. Smart people snooze more because they're less compliant with arbitrary external demands. The alarm is a demand. Hitting snooze is autonomy. It's a cognitive preference for self-determination over social conformity. Evening types are overrepresented in high IQ populations because flexible work schedules select for them, not because of biology. But flexible schedules also mean later sleep, which means waking during different circadian phases, which affects adenosine dynamics and sleep stage distribution. Smart people have better metacognitive awareness, so they notice patterns in their own wake quality and adjust behavior accordingly. Smart people have lower conscientiousness on average, so they're more willing to hit snooze despite social messaging that says it's bad. Smart people have higher working memory demands, which means their prefrontal cortex is more critical to their daily function, which means protecting it during the vulnerable wake transition has higher payoff. And all of this runs on the underlying neuroscience. Sleep inertia is real, prefrontal cortex. Reactivation is slow, adenosine clearance takes time, and snoozing provides that time. In 34 participants awakened from stage 2 and stage 3 sleep showing network segregation collapse, and findings from Scientific American May 1st, 2024, reviewing the October 17th, 2023 Journal of Sleep research study demonstrating that 31 chronic snoozers showed no increased daytime tiredness and improved cognitive performance when allowed to snooze for 30 minutes. Now back to the information. If you're breaking up the last hour of sleep with multiple awakenings, you're preventing the brain from completing full sleep cycles. You're forcing it through multiple transitions. You're accumulating sleep debt. Except the data doesn't support that. Mattingly's study found no difference in total sleep time, no increase in naps, no increase in reported fatigue. Sunderland's study found no effect on overnight sleep architecture, no change in stress hormone levels, no change in mood. The fragmentation concern was theoretical. When researchers actually measured it with polysomnography and cortisol assays and subjective questionnaires, the fragmentation didn't manifest. When someone has sleep apnea, they're getting yanked out of sleep by oxygen desaturations, by gasping for air, by sympathetic nervous system activation. That's violent. That's disruptive. When someone has insomnia, they're waking because of anxiety, rumination, arousal. Their brain is hostile to sleep. That's chronic. That's unsustainable. But when someone hits snooze, they're waking from light sleep. They're falling back asleep immediately. They're doing it in a predictable pattern. And most importantly, they're doing it voluntarily. The brain expects it. The anticipation changes the neurochemistry. The voluntary control changes the stress response. It's not fragmentation, it's oscillation. It's surfing the boundary between sleep and wake. That's 3 or 4 snooze cycles depending on your alarm settings. The cognitive benefits held for that window. But when they looked at 40-minute snooze durations, the benefits disappeared. At 40 minutes, snoozers perform the same as non-snoozers on cognitive tests. There's a sweet spot. Too little snoozing and you wake abruptly from deep sleep. Too much snoozing and you accumulate enough sleep loss that it starts to matter, or you drift back into deeper stages and then get yanked out again. The optimal range seems to be 20 to 30 minutes, 3 alarms, maybe 4. That's enough time for the brain to transition out of slow-wave sleep, enough time for adenosine to start clearing, enough time for prefrontal blood flow to ramp up gradually, but not so much time that you're meaningfully cutting into total sleep duration or risking another descent into stage 3. The snooze button is a tool for people who've hit their sleep quota but are waking at a suboptimal point in their sleep cycle. It's a fine-tuning mechanism, not a compensation mechanism. If you're using snooze as a band-aid for sleep deprivation, you're doing it wrong. Get more sleep. Actual sleep. Full cycles. Sufficient duration. Then if your alarm goes off and your brain is still in a fog, if you're hitting it during a deep phase, snooze can help smooth the transition. But it can't replace the underlying need. Snoozing is weak, but the neuroscience says that's backward. Waking instantly when your brain is in slow-wave sleep impairs your prefrontal cortex for the next 20 to 30 minutes. You're starting the day with degraded decision-making, impaired working memory, reduced cognitive flexibility. If you're trying to do complex work, solve problems, write, code, strategize, you're operating at reduced capacity. The 20 minutes of impaired function could cost you more than the 6 minutes of sleep you lose by snoozing. The trade-off favors snoozing for cognitive workers, for people whose job is thinking. The entire productivity industry is built on the idea that willpower trumps biology, that you can just decide to be a morning person, that optimization means fighting your natural rhythms. The data says that's expensive, fighting your chronotype, forcing yourself to wake abruptly from deep sleep, denying your brain the transition time it needs. That creates cognitive costs. Small costs, 6% here, 13% there, but they accumulate. Over years, over decades, you're operating slightly below your potential because you're trying to conform to someone else's idea of what a good morning looks like. If you hit snooze, stop feeling guilty about it. Set your first alarm early enough that you can snooze for 20 to 30 minutes and still arrive on time. Accept that your brain needs that ramp-up period. Treat it as a feature, not a bug. The alternative is forcing an abrupt transition, paying the cognitive price, then spending the first hour of your day at reduced capacity, probably dosing yourself with caffeine to block the adenosine you didn't give your brain time to clear naturally, creating a chemical dependency to compensate for a behavioral choice you made because society told you snoozing was bad. The old model, snoozing equals bad, sleep fragmentation equals bad, discipline equals good. That model is crumbling under experimental scrutiny. The new model is emerging from polysomnography labs, from EEG data, from cognitive test results. The new model says transitions matter. Brain state at wake time matters. Sleep stage matters. Adenosine clearance matters. Network reactivation matters. And snoozing affects all of these in measurable ways that mostly favor cognitive function for most people in most contexts. Slope. No evidence for that either. Mattingly's data showed stable snooze patterns, not escalating ones. Or they argue that snoozing delays your circadian rhythm, pushes your biological clock later, makes you more of a night owl over time. Possible, but not demonstrated. The circadian system is robust. 9-minute snooze intervals with your eyes closed aren't delivering enough light exposure to meaningfully shift your clock. The sun does that. Your commute does that. The alarm itself, the act of waking, even briefly, sends a signal to your suprachiasmatic nucleus, your circadian pacemaker, that dawn is here. The snoozing doesn't erase that signal. If you're a cognitive worker whose job demands prefrontal function, protecting that function during the wake transition is high value. If you're doing physical labor that doesn't require complex reasoning, the cognitive benefit matters less. If you have a flexible schedule, you can snooze and adjust. If you have to be out the door by 7 sharp, snoozing might create time pressure and stress that outweighs the cognitive benefit. Individual variation matters. Genetic factors matter, personality matters, job demands matter, life context matters. There's no one-size solution. They're the people who've figured out, whether consciously or through trial and error, that the snooze button makes their brain work better in the morning, and the lab data backs them up. 30 minutes of snoozing improves or maintains cognitive performance compared to abrupt waking. It prevents awakenings from slow-wave sleep. It gives prefrontal cortex time to reactivate. It allows adenosine to clear. It preserves functional network segregation. It's a neurological hack, and smart people have been using it all along. The snooze button improved performance. Sleep Journal, October 10th, 2022. 57% of working adults are habitual snoozers. They're not outliers, they're the majority. BMJ Public Health, July 16th, 2024, 26,000 participants. Evening types score 13.5% higher on cognitive tests. The people who wake later, who fight the morning, who hit that button, they're not failing. They're optimizing without accumulating significant sleep loss. The pattern is elegant. It's a solution to the problem of forced awakening in a world that doesn't respect individual sleep cycles. Habitual wake time. They found that snoozing resulted in approximately 6 minutes of lost sleep time, while preventing awakenings from slow-wave sleep stage 3, which is associated with the most severe sleep inertia. The snoozers showed no clear negative effects on cortisol awakening response, morning sleepiness levels, mood ratings, or overall sleep architecture measured across the full night. Most importantly, on cognitive tests administered immediately upon final awakening, the snooze condition either maintained performance equal to the non-snooze condition or improved it, particularly on arithmetic tasks requiring working memory and sustained attention. The researchers concluded that there's no reason to stop snoozing if you enjoy it, at least for snooze durations around 30 minutes, and that it may help people with morning drowsiness be slightly more awake once they finally get up. Laura Peter-Durex and colleagues at Lyon University Hospital published findings in Human Brain Mapping in August 2021, tracking activity in the hippocampus and orbitofrontal cortex during arousals from sleep. They found that wakefulness activity wasn't reestablished instantaneously in the hippocampus. The transition took time. The delay explained why most brief awakenings aren't remembered. If your hippocampus isn't fully online, memory encoding doesn't happen. You wake, you hit snooze, you have no recollection 5 minutes later. The system is operating in a twilight state where consciousness exists, but consolidation doesn't. The researchers found that activity patterns depended on which sleep stage you were waking from. Awakenings from stage 3, slow-wave sleep, showed the longest reactivation times. Awakenings from REM sleep were faster. Stage 2 was intermediate. The brain state at the moment of awakening determines the trajectory of the recovery. If you're in deep sleep when that alarm hits, you're forcing your hippocampus and prefrontal cortex through a longer, harder transition. If you're in light sleep, they're already partway there. The snooze button becomes a tool for timing. You're gambling that the next alarm, 9 minutes later, will catch you in a better state. And the data suggests that gamble pays off more often than not. It's a collection of brain regions that activate when you're not focused on the external world. When you're daydreaming, reminiscing, planning, mind-wandering, the default mode network lights up. It includes the medial prefrontal cortex, the posterior cingulate cortex, the precuneus, parts of the temporal lobe. During focus tasks, this network should quiet down, suppressed by task-positive networks like the dorsal attention network. But during sleep inertia, the default mode network doesn't shut down properly. It stays hyperactive. It intrudes into waking consciousness. That's why you feel spaced out, unfocused, like your thoughts are drifting. Your task-positive networks are trying to come online, but the default mode network is still running the show. Default mode network and task-positive networks was the neural signature of sleep inertia. In a fully awake brain, these networks anti-correlate. When one activates, the other suppresses. They're antagonistic. But right after waking, especially from deep sleep, that relationship breaks down. Both networks are partially active. Both are partially suppressed. The functional segregation is lost. Your brain is trying to be in 2 modes simultaneously. Introspective and focused, resting and alert. It doesn't work. Performance suffers. And it takes 15 to 20 minutes for that segregation to reestablish. You reach functional segregation sooner. The cognitive tests support this. Sunderland's snoozers didn't show the same performance decrements. Their brains were closer to fully awake architecture right from the start. For adenosine-sensitive people, snoozing might be essential. Their load is higher, clearance takes longer. GG variants clear adenosine faster naturally, need less snoozing. The snooze button became common only in the 1950s. Chronotype dominates all other factors. The UK Biobank study from Imperial College tracked actual sleep timing, wake times, cognitive test performance. Evening types scored 7 to 13% higher depending on cognitive domain. Morning types scored lowest. Intermediate types fell in between. The gradient was monotonic. Later preference meant higher scores. If you're a night owl forced to wake at 6 a.m., you're waking at the wrong circadian phase. Your cortisol hasn't spiked, your core temperature is at its nadir, your melatonin is still elevated, the sleep inertia will be worse, the prefrontal reactivation slower, the adenosine load higher. Snoozing bridges the gap between when society demands you wake and when your biology is ready. Their cortisol is already rising, their body temperature climbing, their melatonin shut down, they're aligned. They don't need to snooze because they're waking at the right phase. They feel virtuous and tell others to have more discipline. But chronotype is 60% heritable. The PER3 gene, the clock gene, multiple loci in genome-wide studies. You can't turn a night owl into a morning lark. They score higher on cognitive tests. They're overrepresented in creative fields, research, entrepreneurship, domains with schedule flexibility. The correlation isn't simple causation, but smart people end up in jobs that allow later waking, and later waking preserves cognitive function. The snooze button is part of that preservation system. Where school started at 10 a.m., where societal schedules accommodated evening types instead of morning types. In that world, who would snooze? Probably morning types. They'd be the ones forced to wake later than their biology wants. They'd be the ones fighting grogginess, dealing with sleep inertia, needing extra time to transition. The phenomenon isn't about intelligence per se, it's about mismatch. It's about what happens when your alarm goes off at the wrong phase of your personal circadian cycle. The smart people snooze more because they're the ones most likely to have evening preferences and the ones most able to recognize and respond to their own biology rather than blindly following social rules. Balkan's work using PET scans showed soldiers woken suddenly had diminished prefrontal cortex function for 15 to 20 minutes. That's a security risk. The solution wasn't demanding more discipline, it was changing wake protocols. Use gradual light, sound, temperature changes, ease the transition instead of forcing it. We glorify instant wake-ups, shame snoozing, structure workdays around morning, start times misaligned with population chronobiology. We lose productivity, innovation, cognitive performance. The 6 to 13% deficit compounds daily. Decisions slightly worse, problem solving slightly slower, creative insights slightly less frequent. Over years, over careers, the loss is enormous. The real solution is schedule flexibility. Let people work when their brain works best. Let people wake when their biology is ready. Let evening types start at 10 a.m. or noon, or whenever their cognitive function peaks. Let morning types start at 6 a.m. if that's when they're sharpest. Optimize for performance instead of conformity. But until that world exists, the snooze button is the tool we have. It's a small rebellion, a small optimization, a small acknowledgement that your brain knows better than your alarm clock when it's ready to think. The default mode network taking its time to segregate from task-positive networks. The adenosine taking its time to clear from receptors. Every system has a timeline. Every transition has a cost. Snoozing reduces that cost by spreading it across multiple wake attempts instead of forcing one brutal jump from deep sleep to full alertness. 31 people across multiple nights, comparing nights when participants snoozed for 30 minutes versus nights when they woke immediately at their habitual wake time. They found that snoozing resulted in approximately 6 minutes of lost sleep time while preventing awakenings from slow-wave sleep stage 3, which is associated with the most severe sleep inertia. The snoozers showed no clear negative effects on cortisol awakening response, morning sleepiness levels, mood ratings, or overall sleep architecture measured across the full night. Most importantly, on cognitive tests administered immediately upon final awakening, the snooze condition either maintained performance equal to the non-snooze condition or improved it, particularly on arithmetic tasks, requiring working memory and sustained attention. The researchers concluded that there is no reason to stop snoozing if you enjoy it, at least for snooze durations around 30 minutes, and that it may help people with morning drowsiness be slightly more awake once they finally get up. It knows when you can think clearly immediately and when you need time. Trust that knowledge. The alarm clock doesn't know your sleep stage. The alarm clock doesn't know your adenosine levels. The alarm clock doesn't know your prefrontal blood flow status. Your brain knows all of it. When your hand reaches for that snooze button in the fog of morning, that's not weakness. That's your brain protecting its most valuable resource, cognitive function. Let it.